We have finished discussing the binary Huffman procedure. We now discuss the Diary-Huffman procedure. In this procedure, the smallest d probability masses are merged in each step, forming an internal node of the resulting code tree. If the resulting code tree is formed in k plus 1 steps, then there will be k plus 1 internal nodes and d plus k times d minus 1 leaves, where each leaf corresponds to a source symbol in the alphabet. If the alphabet size has the form d plus k times d minus 1, then apply the Huffman procedure directly. Otherwise, add a few dummy symbols with probability 0 to the alphabet in order to make the total number of symbols have the form d plus k times d minus 1. Here is an example with d equals 3 and k equals 2. And this is a possible code tree. In the Huffman procedure, the number of steps is equal to k plus 1 equals 3, and that corresponds to the formation of the 3 internal nodes. The number of leaves is equal to d plus k times d minus 1, that is 3 plus 2 plus 2 equals 7. We now discuss an upper bound on the expected length of a Huffman code. Theorem 4.18 says that the expected length of a Huffman code, denoted by LHuff, satisfies LHuff less than hd of x plus 1. This bound is the tightest possible among all the upper bounds on LHuff, which depends only on the source entropy. Here is the proof outline. First, we construct a code with covert lengths Li equals the ceiling of minus log d pi by showing that the Kraft inequality is satisfied. Then we show that the expected length of this code, summation I pi Li, is less than entropy of x plus 1. Then LHuff, which is the expected length of an optimal prefix code, must be upper bounded by L, which in turn is less than entropy of x plus 1. We now prove the upper bound on the expected length of a Huffman code. Consider constructing a prefix code with covert lengths Li, where Li is equal to the ceiling of minus log d pi. Because Li is the ceiling of minus log d pi, it is at least equal to minus log d pi and at most equal to minus log d pi plus 1. Note that the second inequality is strict. Multiplying by minus 1, we have log d pi greater than or equal to minus Li greater than log d pi minus 1. Or pi is greater than or equal to d to the power minus Li greater than d to the power minus 1 pi. Now using this upper bound on d to the power minus Li, we have summation I d to the power minus Li less than or equal to summation I pi, which is equal to 1. That is, Li satisfies the Kraft inequality, which implies that it is possible to construct a prefix code with covert lengths Li. It remains to show that L, the expected length of this code, is less than hd of x plus 1. Consider L equals summation I pi Li. Using this upper bound on Li, we obtain the strict upper bound summation I pi times minus log dpi plus 1. And this is equal to minus summation I pi log dpi plus summation I pi. The first summation is simply the entropy of X in the base D, and the second summation is just equal to 1. Thus, we conclude that L half, which is upper bounded by L, is strictly less than Hd of X plus 1. To see that this upper bound is the tightest possible, we have to show that there exists a sequence of distributions pk such that L half approaches Hd of X plus 1 as k tends to infinity. This can be done by considering the sequence of DRE distributions P sub k, which consists of, first, the probability mass 1 minus d minus 1 over k, and then d minus 1 copies of 1 over k, where k is greater than or equal to d. The Huffman code for each pk consists of d code words of length 1, because they are exactly d probability masses. Thus L half is equal to 1 for all k. This is shown in the figure. As k tends to infinity, Hd of X tends to 0 because pk tends to the deterministic distribution. And hence, L half approaches Xd of X plus 1. The theorem is proved. To end this section, we discuss the asymptotic achievability of the entropy of X. We have seen that the expected length of a Huffman code is lower bounded by the entropy of X and is upper bounded by the entropy of X plus 1. Now consider using a Huffman code to encode x1, x2 up to xn, which are n IID copies of a generic random variable X. Now for these n random variables, the entropy is equal to n times the entropy of X. Then this big Huffman code with expected length L half sub n is lower bounded by n times entropy of X and upper bounded by n times entropy of X plus 1. Divide by n to obtain 1 over n times L half sub n greater than or equal to entropy of X and less than entropy of X plus 1 over n. Note that the right-hand side of this inequality tends to entropy of X as n tends to infinity. This quantity 1 over n times L half sub n is called the rate of the code, in dit per source symbol. This is on average the number of DRE code symbols required to encode a source symbol. The above inequality simply says that as n tends to infinity, the coding rate can approach hx, the entropy of an individual source random variable. Thus, in the asymptotic sense, the entropy of X is the fundamental measure of the amount of information contained in a random variable X.